Trigonometry, Chapter 3, Radian Measure and the Unit Circle, Section 4, Linear and Angular Speed, Video 2, Connecting Linear and Angular Speed. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we learned about calculating linear speed and angular speed. In this video, we will explore the connection between the two. Recall the following. If an object travels a distance of d over time t, then the linear speed of the object is v equals d divided by t. And if an object rotates an angle of theta over time t, then the angular speed of the object is omega equals theta over t. Left out the word the here. Can we connect the two? In order to do this, let's clarify what exactly we're trying to accomplish. Suppose you have a rotating disk of radius r. On the edge is a point P that rotates through a central angle theta radians over time t. So this point is rotated this many radians over a certain time. What is the linear speed of P? What is the angular speed of P? And what is the relation between the two? First, let's set up an expression for the linear speed. To do this, we need to know how far P traveled. That's equivalent to asking the length of the arc in red. Use the arc length formula, S equals r theta. Remember, theta is in radians. So the arc length is just r times theta, the distance traveled. Since the time required was t, the linear speed of P is velocity equals distance over time. So the distance was the arc length, r theta, divided by time. There's our expression for the linear velocity of a point on this rotating disk. The angular speed is easier. It's just the angle divided by the time. So omega equals theta divided by t. So we have v equals r theta over t and omega equals theta over t. We can solve the second equation for theta. This should say theta. I'm not going to stop and fix everything right now. I'm just going to cross this out and put theta. We can solve the second equation for theta and substitute the result into the first equation. Now it makes me wonder if this typo carried over. It did not. I fixed it here. All right, so the second equation, if we solve it for theta, we simply have to multiply both sides by t to get theta equals omega t. But now we can substitute this into the first equation. So we're going to take the omega t and we're going to substitute it for the theta right there. And when we do, we will get something that looks like this. Velocity equals linear velocity equals radius times omega times t divided by t. But the t's cancel, and this simplifies to velocity equals r times omega. That is our equation that connects the two. If a point on the edge of a circle, a radius r, has a linear speed of v, then the circle has angular speed omega, then v is equal to r times omega. In order for this to be true, however, the angular speed must be measured in radians per unit time. The derivation of this equation used the arc length formula, which requires the angle to be in radians. So keep that in mind. Recall the tennis player from the previous video who swings a racket through a 90-degree angle in just 0.045 seconds. If the distance from the wrist to the tip of the racket is 2 feet, find the linear speed of the tip of the racket in miles per hour. From the previous video, we calculated the angular speed of the racket as angular speed is theta divided by time, which was 90 degrees divided by 0.045 seconds, which was 2,000 degrees per second. But then we converted it and got approximately 34.51 radians per second. Remember, everything has to be in radians for these comparisons between linear and angular velocity to work. To find the linear speed, we just multiply r times omega, because that's our formula. Well, the radius is 2 feet, and the omega is 34.51 radians per second. This will give us, oh, wait a minute, radians is unitless, so we can ignore that. And we can convert to miles per hour. So we need to set up the conversions there. Set up 1 mile per 5280 feet to cancel the feet. Set up 3600 seconds per 1 hour to cancel the seconds. Radians again are unitless, so we can ignore it. That will give us miles per hour. Put it all in the calculator, and we get that the tip of the racket is swinging at about 47 miles per hour. Now you try. Pause the video and try the following. All right, here's your fair warning if you have not yet paused the video to try the problem. Solutions in 3, 2, and 1. Notice I did do the conversion to radians in the midst of the formula, as well as the conversion to miles per hour.